4 to the crowd. Okay. All right. All right. All right, we got 10 more seconds of awkward silence. We're just not very silent right now, but all right. So it is time to get the lecture started. It has been recording already. Um, so I'm gonna start with any questions about the homework? Yes, go ahead. Mm-hmm. Yep. So the whole point of the homework is to get you to think about it. Okay. So this is the homework assignment. It is okay. First of all, when is it due? Yes. Okay. Very good. All right. So the last three questions, starting with question number 6. So it is asking regardless of, is this always true? In other words, we are asking about this implication here. Okay, this implication operator, is it always true or is it always false? Or it kind of depends on the sets, A and B. So the way to answer this question is to come up with examples and to understand what it takes for an implication to become true, what it takes for an implication to become false. So you have to go by the definitions and then start thinking about the whole thing. So there was a hand, I think that was Elia. Yeah, go ahead. Okay, let me let the other person in. Give me a second. So in this case, I cannot answer the question, obviously, because this is your homework. So the way you look at this is to think about what does it mean when A minus B is an empty set. Okay, so that's a symbol. Okay, so you have to go back and understand what the symbol means. What is A minus B when A is a set and B is also a set? What does it mean when it is an empty set? And then on the right-hand side, we have A is a proper subset of B. So the key is proper subset and not just subset of, but there's a negation in front of it too. So there's this little negation here. So the idea is you want to give yourself a bunch of examples, like what if this is A and what if this is B? What if this is A and what if this is B? And so on and so forth. Okay. So you want to experiment with different types of A and B. Some will give you an empty set when you look at the difference, and some will not give you an empty set when you look at the difference. Some will give you an answer of true when you evaluate whether A is a proper subset of B, and some will give you a false when you ask whether A is a proper subset of B. So you have to evaluate all of those possible options, okay, on both the left-hand side and the right-hand side, and then see if you can find a pattern, okay? So the next one is very similar in nature, okay? So the key here is to understand how the operators are nested. So this is the last operator. Once again, it is an implication, which means it is super duper important to understand well, when does an implication give you an answer of true, and when does an implication give you an answer of false? There's only one scenario, it will give you an answer of false. For all the other three scenarios, it will give you an answer of true. So now you have to, once again, look at um, different situations where the intersection between A and B and the union between A and B are exactly the same, and look at cases where that is not the case. And then you also want to find out cases where A and B are actually the same set, and when A and B are not the same set. So and then look for a pattern. Yep. So do not disclose the answer. No spoiler in this class. Otherwise, I'll give the person who disclosed the spoiler a 0, even though it is clear that that person know the answer. But because that person enables other people to cheat. In fact, that person is forcing the rest of the class to cheat. So that person, it will take the hit for the entire class. So that will be a negative, whatever the number is, times the number of people in the class. That would be the proper treatment. That would be, I would say that is a proportional consequence. So it would be nicer to have a smaller class in that case. So do not disclose. Don't tell me the answer. Do not spoil. Okay, because the whole point. Huh? Say again. Does the what? Oh no. Just don't do it. And we have one more person who wants to be online. So I will admit that person and then mention that unless there's an agreement to. All right. So okay. So this message is directed to people who are online, unless you have an agreement with me that you will be absent on a particular day for a good reason, and I give you the permission to attend the class online, you have to be in person. Otherwise, I will count those people as absent. So there you go. And I think one of these people have not given me a reason to be attending via Zoom. So, yep, that's going to be the case. All right. So getting back to these questions. Yep, go ahead. You can still continue. Yep. Mhm. Yep. As long as you do not submit, you have until the due date to turn it in. Yep. So that means, think very carefully, before you click the submit button. As long as you have not submitted yet, you can still kind of think about it, go back, change the answer, and so on. Okay. So the last one is kind of the same deal. Think of situations where A as a set is actually an element of B. Think of situations when that is not the case. Think of situations where A is a proper not a proper, A is a subset of B, and think of cases where A is not a subset of B, and then you look for the pattern. Once again, the implication is the final operator. So, you really have to know, the truth table corresponding to implication as an operator. All right, so we'll be good with the homework assignments. Okay, very good. And then we're gonna move on to, yes, one of the practice. Okay, give me a second. Let me go back to the notations. So we are talking about, okay, which one? Mm-hmm. Hmm. But it is in the module. All right, so we'll take a look. All right, so let's check out. uh, Not this one. Okay, number 4. Okay, All right, so this one says express the following in symbolic form. There exists at least one even number in the set 1, 2, 3, 4, 5. Okay. Oh, okay, sorry. Express the following in symbolic form. Not every student in the class passed the exam. So that means there exists one person who did not pass the exam. So you can basically say, okay, let's say predicate P is sets that person either pass or not pass the class because you can always use a negation to negate it, and then you can now say there's a particular set. Let's just say C. C is the set of people who are in the class. So now the way you express that is there exists student S in C in parentheses such that that person did not pass the class. Yeah, there are two possible answers. Mm-hmm. Sure. Okay. Okay. I will do that. Let me see if Ilya has a good point to make. Go ahead. Okay. So I'm starting Joplin right now, just so that I can kind of record this into Joplin. So we'll try to make everything visible, which is kind of a chore, but it's doable. All right. All right. So I'm just gonna put some empty space here, and I'm gonna quote the sentence. Not every student in the class passed the exam. Okay. So a few symbolic things that we have to deal with first. Okay. So we'll say let P of X be the predicate that returns true if and only if X passed the exam. Now you can reverse this one easily, right? Because you can just put a negation. But P of X means the student passed the exam. Let me scroll on the other side because you guys are reading on the right hand side, not the left hand side. There we go. Okay, and we'll say let the set of all students in the class be C for class. Okay, so now the question is, how do we express the sentence of not every student in the class passed the exam? So the problem with natural language is the nesting is not always obvious. Okay, so in this case, we can also basically we say it is not the case that every student in the class passed the exam. So obviously, people don't say things like these with parentheses, but the parentheses obviously help to emphasize the negation is on the statement that everybody, every student in the class passed the exam. So if you choose to interpret it this way, which is fine, one of the alternatives, then it is okay, so I'm gonna scroll on this side. Okay, there we go. So you can say, okay, it's the negation of something, right? Because this negation, this not applies to this entire thing. So now what is left is to express every student in the class passed the exam in the parentheses. So now that would be a universal quantifier because all, they're all universal. And then there exists some, at least one, they are existential. Okay, so in this case, it is universal. So now we have a for all, and I will use S for student. And I'm going to use the short form for all S in C, which means every student in the class blah what do we want to express in this case. So now inside the parentheses we have to make use of the predicate P, but we already mentioned earlier that the predicate P means P of X is true if and only if X pass the exam, right? So in this case we also want to express just P of S in this case, because inside the parentheses, we want to express every student in the class passed the exam. So this is one way to express that. Yes, yes. So you can use existential, but the existential would be a little bit different. So we'll start with the way we express it in natural language first, and then we'll reverse it. Yep. So we can now say that sentence is also basically saying at least one student in the class did not pass the exam. Okay, so I'm just going to pause here first, just to make sure that everybody can associate that this statement, at least one student in the class did not pass the exam, is the same thing as not every student in the class passed the exam. So are we okay with that? Yes. No. Yep, very good. So in English or in natural language, we re-express it and go like, oh, okay, if we say not everybody passed the class or passed the exam, then it means at least one person did not pass the exam, right? So now we look at this and then we put parentheses around the whole thing. Okay, so I will, oh, wrong window. Here we go, copy and paste. So this time, the only thing I'm changing is put parentheses so that we can kind of express the nesting of the statement. So this time the quantifier is not negated. At least one student in the class, okay, that is not negated. What is negated is inside the parentheses because the predicate says P of x is x passing the exam. Now we have to express the negation of that. So that means when we translate that into the mathematical form, then it becomes something like this. It starts with there exists a student in class C. Okay, that's so basically this part, okay, this entire part here, or from your perspective, this entire part is is basically there exists a student as in the class C such that well, the such that is did not pass the exam. Okay, so the way we express did not pass the exam is the student S, okay, which is a variable bound to a certain student. We just go like, it is not the case that this person passed the test. So that's the alternative to express that. Does that make sense? Mm-hmm. Very good. Okay, so imagine that the class only has two students. Okay, so we have mm, person X and person Y, okay, as in the class. I hesitated a little bit because I was told that I need to be more uh, equal when it comes to using names. So I have to use names from both different culture. But since I'm not really familiar with names to begin with, so I'm just going to use X and Y. Then nobody can complain about it. Okay, so if we only have two students, X and Y in the class, okay, so let's just say that, so I'm going to put in here. So let's assume the class C only has two students, X and Y. Is that okay? So what does it mean when the entire class passed the test? In other words, how do we express? I don't know why it doesn't like that. It's probably because, nope. Okay. So the entire class passed the exam is the same thing as saying P of X and P of Y. Does that make sense? Okay. So when you want to say, at least one person did not pass the class, you're negating this entire thing because you're saying it is not the case that the entire class passed the exam. Yes. Well, just give me a second here. Okay, so we're gonna do some Boolean algebra here. So now you can say, what about that is not the case? Well, that's an easy one because all we need to do is to put a negation here and around the entire thing. Is that okay so far? Okay, that should be fairly straightforward because we are just negating the fact that the entire class passed the exam. Okay, so from the linear algebra perspective, now we can apply what we call the De Morgan's law. Okay, so De Morgan's law is really interesting. So I don't understand why sometimes it would skip an empty line and other times it does not. Okay, so we'll go ahead and early introduce De Morgan's law a little bit earlier than usual. Okay, so De Morgan's law, there are two parts to it. The first part says, okay, so this is something that we'll look at again. So the first part says the negation of I cannot use x, y, a, b. We can use j and k. Okay, so j and k is the same thing as I'll fix the formatting once I close the dollar sign. So it's the same thing as the negation of j or the negation of k. Okay, that's one part of De Morgan's law. In other words, this equality always holds. Okay, so De Morgan's law means the law itself is always true. So does that make sense to you? That it is not true that the conjunction J and K is true. Does that mean not J or not K? One of them is not true. At least one of them is not true. It kind of makes sense, right? Okay. For those of you who are not convinced about De Morgan's law, what are you going to do? Truth table, very good. Okay, so make your truth table where J can be true or false, K can be true or false. It has 4 rows. Work out all 4 rows. One using the negation of J and K, the other one using not J or not K, and observe that all 4 rows end up with exactly the same values for the two expressions. Okay, it is a good way to practice the use of a truth table, but it is always a good way to learn De Morgan's law because the moment you finish the truth table, you go like, oh, okay, it is without a doubt that the two expressions are the same. Whether you understand this equality intuitively or not, the truth table is conclusive. It just says, yes, they are exactly the same, even if it does not make sense intuitively for certain people. Yes. Hmm? Yes, it would be the same thing as an and because it is the negation of and on one side. But there's a counterpart to this rule. Okay, so De Morgan's law has two parts. So the other part looks kind of the same, except everything is reversed. Well, I shouldn't say everything, but the operators are reversed. So where we had and, it becomes an or. Where we had or, it becomes an and. So once again, it may not look intuitive to you. And for those people, I highly recommend that you finish the truth table so that you can show it to yourself. Okay, I am now convinced 100% that these two expressions are the same. I have no idea what people do with my recommendation, but then it is not my grade at the end of the semester, and it is also not my career 4 years from now, or maybe 2 more years from now. So my recommendation is based on what I understand, how people learn, and what can be beneficial. But whether people do it or not is out of my control. But I recommend people to do the truth table for both of these expressions. Then you can see it for yourself that they are actually the same. So what does this have anything to do with existential versus universal thing and how we apply the negation? Well, it is just looking at this thing here, and now with De Morgan's law, I can now transform not the entire class past the exam, which is the negation of P of X and P of Y as a whole thing. Now I can apply De Morgan's law and say, oh, it really is the same thing as saying, which one should I apply? This one here, not P of X or not P of Y. But that's existential because in the existentially quantified expression, if at least one thing is true, the whole thing is true. Okay, let me actually write it out. Okay, so using De Morgan's law, okay, now I can rewrite the entire thing, which is basically saying, okay, let me transform the expression first, and then we'll put it back into a quantified expression. So that means the negation of P of X and P of Y is the same thing as the negation of P of X or the negation of P of Y. Okay, let me finish the whole thing, scroll up. Okay, is that okay? On the left-hand side, this is what we had earlier. On the right-hand side, this is the result of applying De Morgan's law. So are we okay with that transformation? The application of De Morgan's law. Yes. Hmm? Well, I mean, if one is false but the other one is true, then it is still the whole thing is still true because in between we have a disjunction. Yeah. So now we look at this and go like, and then we say here, okay, once again, it leaves one empty line where it's not supposed to be. But then we can say, oh, but this is the same thing. This is the same as saying there exists. Okay, I'll put it in words first. Okay, I would say at least one of X and Y did not pass the exam. Okay, is that okay? I'm talking about the right-hand side of the equality. When you look at the right-hand side of the equality, does that give you the same meaning as it is the same as saying at least one of these two did not pass the exam? Yep. I cannot hear you, sorry. All right. So this is important because when I introduce these symbols, sometimes the definition can scroll off from the screen. So it is important that you take notes when I write something like this. So that way you can reference in your own notes how P is defined. So taking notes is important. Not because I specifically want to make it so difficult that you cannot take this class without taking notes, but because the screen is only so big. I cannot maintain everything to be on screen at the same time all the time. Yep. Hmm? Can you use what? Yeah, sure. Yeah. As long as it is defined, it's fine. But the whole point of this entire discussion is now I transform the entire thing back to at least one, okay, which is existential quantifier. X and Y did not pass the exam, which is P of something is false. But this is the relationship between the quantifiers and the two logical operators, and versus or. And is used when we have a universal quantifier, or is when we use the existential quantifier. And because of De Morgan's law, you can always transform from using one to the other one when you have a negation. It's just a different way of looking at things. But as you said, a certain form makes more sense to you intuitively, but from the mathematical perspective, they are equivalent. So does that kind of help address that whole thing? Mm-hmm. Oh, okay. So okay, I think I see what you mean by that. So you are asking about the transformation of the shorthand, which is okay. So I use a shorthand in this case, which is for every student S in C, in this case, P of S. Okay. So that's one form, okay, to say that everybody passed the test. And this is a shorthand is the same as this one here, which is for everything in the entire universe, S, okay? S being in C implies P of S is true. So are you referring to this implication? Okay, so the purpose of this notation, because most of the time, okay, you have certain predicate or certain Boolean expression to evaluate, but it doesn't really, you don't want to apply that to everything in the entire universe, okay? You want to apply that only to certain things that are of concern to you, right? So the notation is just a shorthand to say, okay, C is a set of all the things that are of concern to us. Okay, we only want to apply P of S to the things that are of concern to us. Is that okay? But to express that using the actual truly, true universal quantifier for all S means for everything in the entire universe. So that means it includes all the other things that are of no concern to you. So this is a filtering mechanism. S is an element of C implies something. It's a filtering mechanism. Because for things that are not in C, things that are of no concern to you, the left-hand side of the implication becomes false, which means the implication is true, which means it does not change the default value or the actual useful value of for the quantified expression. For things that are actually in C, okay, those things because the left-hand side of the implication is true, then it really just depends on the right-hand side to see whether the implication is true or not. So it is used as a filtering mechanism. If you change the implication to an and, that means for everything that are of no concern to you, the conjunction will return a false. But if you have at least one false for the entire quantified expression, the whole thing is going to be false. So if you are to change this implication to an and, it means the entire quantified expression is likely to be false. Does that make sense? Yeah. So it is a filtering mechanism where the implication means the quote unquote default value for things that are of no concern to us is the identity of conjunction. So it doesn't change the useful or the meaningful outcome of what you really want to express. Is that okay? Okay. All right. I like these discussions, because it takes thoughts and kind of studying and reviewing on your part to come up with these questions. So that's a reflection that people have been studying and at least kind of knowing on the material. A lot of this stuff it's not something that you can just learn like programming, okay, because there's nothing to test it. But you have to gain an understanding, and to gain an understanding is to look at these things, ask questions, and attempt to answer those questions by yourself. And if you cannot answer those questions, then bring it up in the class so that we can talk about it. All right. Any other questions? No other questions? Okay. So without any additional questions, and it is also, I think it also proves a point of these questions that I include in these modules can be helpful, okay, because they really get you to think about things. And all of these are generated by the AI. And many times I would actually give you the prompt of how to generate these questions, not this one, but it's very similar. Okay, all of these are generated using about the same prompt. I use ChatGPT. Obviously, you can use whatever LLM that you want to use. You can download DeepSeek on your own computer and then just run it locally. Okay, that's fine too. I have not tried it with DeepSeek to see whether it can actually generate output similar to these, but these are from ChatGPT and it works okay. Yep, number six. Okay, so let's go take a look at number six. All righty. All right, convert the following to natural language. Well, I think that's something that it basically it's the same thing as saying there exists one thing in the entire universe, at least one thing in the entire universe, that P of X is false. Hmm? Well, we don't know what P is, but if you look at the answer, it says there's at least one X such that P of X is not true. And I don't know why it is formatted like this. I think it's because of the actual, it's a formatting error. So let me look at the tag command here. At least one X such that P of X is negated. Okay. I have no idea why it is. This is AI generated, and that's one of the problems with AI generation. So the answer would be there's at least one X such that P of X is false. So very good. Bring it up, and I'm going to fix it. If you see something that like this, you can always change it yourself too. So just go to the bottom, go to here, improve this page, and then go to that particular example. It's question number 6. Okay. All right. So this is number 6. The actual answer is much longer than the one that we saw, and it's cut off. Okay, I know what's going on now because the formatting. So this is something about Markdown, and also it's the interaction between Markdown and Jackal. Jackal is the engine that translates from Markdown to HTML, and everything that is in an HTML tag is not interpreted by Markdown. So I have to say Markdown equals to 1 as an attribute so that it would actually understand that it has to do the translation. All right, good catch. So if you guys see something like this, the answer does not make sense, just let me know and I will go ahead and fix it. And it's going to take a minute or so for it to bake. Okay, so it's going to, where's my, all right, so there we go. We go back here. So we give it a minute or so. Any other questions? All right. So I think the key takeaway is to understand that a universal quantifier, the for all, is an implied huge conjunction. The existential quantifier is an implied huge disjunction. So I think that's the main takeaway for this part. All right, so I'll give it maybe one refresh and see whether it is fixed. Yep, it is now fixed. It's just because I did not tell it that the enclosed text inside that HTML element is an HTML is in Markdown. It just did some funky stuff and cut off certain things. All right. Any other questions? Yep. Okay, you first, and then you. Go ahead. No, a predicate is no more than just a function that returns a value that is either true or false. And when it returns true and when it returns false really depends on the context of how you want the predicate to be expressing, what you want it to express. So in the example that we have been talking about, you mean this one? I Question 6 does not tell you anything about what it means. It just says there's a predicate P. So it is not about the predicate P. It is about how do we express it in natural language, because that's what that's what this syntax specifies. We are only concerned about the equivalent expression in natural language and not so much the actual meaning of the expression. So it's more like a format thing. You look at this format and you equate it to this. Okay, so okay, I need to turn that off. You guys cannot hear because it's here. Okay, okay, it's gone. Okay, you guys cannot hear it, but over here it keeps incoming call like 6 times in a row. Yeah, it's okay. So whatever is inside this pair of parentheses, inside the for out. Okay, after there exists x, whatever is inside the parentheses is an expression that you have to evaluate for everything in the entire universe. If at least one thing in the universe makes that expression true, then the entire quantified expression is true. That's the definition of an existential quantifier. It really is just the definition. Then you just have to say it's negated. Yeah. Are we good? Okay. Go ahead. P of x just returns a value that's either true or false. So we are not concerned about how P is defined in this case. We're only asking, can we look at the mathematical notation here and understand that the sentence, is what it means. Yep. Okay. Mm-hmm. Okay. So let me try to track what you said. Okay. Go ahead. What was the sentence again? Well, okay. So okay. Let me try to type what you just said. Okay. So go ahead. Okay. There exists one thing X in the universe. Uh-huh. Okay. Mm-hmm. It's false. No. So these two are not the same. In fact, one is the opposite of the other one because there exists one thing in the entire universe is this part here. Okay. So that P of X is false is this part here. we P of X itself returns either true or false, right? So that means the correct answer to what you said is you need a negation here. P of X can be true or false. It's just a Boolean function. That's all it is. It is a Boolean function. It returns a value that is Boolean. But it is okay. So this is the part where the abstraction of this class is kind of getting into the way, because our focus is not even how P of X is defined. Our focus here is if you are given a sentence and you need to look for the equivalent expression in using mathematical symbol, what does it look like? So it is more of a syntactic kind of nature, than it is of a semantic nature. Yep. Mm-hmm. Yeah. Yeah. But I think this is better. Okay, it more closely resemble the English sentence, because in the English sentence I put extra parentheses in order to indicate the nesting. There exists one thing in the entire universe, so that's just compactified to these two symbols, the inverted E plus the X. Is that okay? That is just the notation. Okay, and then the so that, okay, such that is the parenthesis, outermost parentheses. P of X is false. P of X is false. But P of X is false is the same thing as saying not P of X. Yep. Nope. There's nothing concrete here to use a truth table on. Oh, that I can show you. Okay, so because I wasn't sure about what the truth table was for. Okay, so let's look at the truth table here. Okay, yes, go ahead. It's more like a notation more than anything else. Given the what you want to say using natural language, what does it look like in mathematical notation? So it's more of that nature than anything else. But I can do this. Okay, this I can do. Okay, this is concrete. All right, so since x is a Boolean variable, so it can either be true or false. So that means I just need one row for false. All right, so on the row for false, what is not x, the negation of x? True. And then what is x equals to false? When x is false, false is true. Very good. Okay, excellent. So now we have to answer the question of what if x is true to begin with? Not true is false. And then if x is true and we are asking does true equal to false? What is the answer to that? No, false. False does not equal to true, or I should say it is false that false equals to true. Does that make sense? Are we good? Have we established the negation of x is the same thing as saying x is false? All right, excellent. So I think that was part of the core of the original question. Yep. It doesn't matter because x here is really just a placeholder of something. It can be a single variable, a Boolean variable. It can be P of E. It can be a gigantic expression. It doesn't matter what it is. It's just a placeholder to say that if that placeholder is false, then the negation of that entire thing has to be true, but it is also the same thing as comparing that entire thing to false. All of these are in C++ as well. Okay, so this is not something new, except in C++. Okay, so let's look at the expression in C++. Yeah, go ahead. Yes. Yep. But in C++, okay, in case you do not know, which will be of that would concern me. Okay, it should concern you if this is not something that you already know. Now, which way you use doesn't matter, okay? Whether you have a preference to say negation of x in a Boolean expression or you say x is false, that's up to you, okay? That's a style thing. But not knowing that these two expressions are exactly the same in the context of x being a Boolean something, that would concern me, okay? I'm just going to be brutal in these things because it's better for me to be brutal now that you guys realize, oh, I might need to go back and review some of the material from CISP 360, okay, than not knowing that there are certain things that you should have gotten in CISP 360 that you have not gotten. Okay, so that's just me, the way that I teach my classes. Because unlike some of your other professors, I'm not here to make you happy. And many other people say, Tech, you cannot say that in the class. Why not? I'm here to get you guys ready for the next class, which is not even going to be here. Okay, this material is not needed for any class that you will ever have to take in Los Rios. It is going to be upper division classes at a 4-year university. Okay, so I just want to kind of put everything in context. Are we okay so far? Okay, all right. Any other questions? I think all of these are good questions, because it means you guys have spent the time to really think about these things and think about, okay, what does that actually mean? And that's good. Okay. And I'm here to kind of help you address and how to relate what you're learning here to things that you have learned already. Okay. Or supposedly. All right. Are we good? Okay. All right, so then we shall move on to talk about injection and bijection. But before we go there, let me remind people that you have one homework assignment due on, where is it? Set notation is due on the 12th, which is Wednesday, right before class. And then we have another new homework assignment, which is just functions, and that is due on the 19th because we do not have class on Monday. Monday is a holiday, so we are losing one day, because of that, at least one day in the semester. So that's why the due date is not 1 week from today, which is usual for me, is one day, 1 week from the day that I assign it. But because we are not meeting on next Monday, I'm making the due date next Wednesday. Yes, question? No? Hmm? That is correct. The whole campus will be closed on the 17th. But when the campus is closed, it just becomes a public place. You're more than welcome to park in the parking lot and just have a stroll on campus. Except I won't be here. There won't be any classes. Is that okay? Are we good? Okay. All right. So we are basically done with functions as sets. Okay. But I am going to reopen this tab here just to make sure that all the concepts are cleared, particularly the last one, which is what makes a function a function. So the first thing that makes a function, if f needs to be a function, the first criterion is it has to be a subset of the Cartesian product between X, which is the intended domain, and Y, which is the intended codomain. Now, which one is intended as what is expressed here? So this thing here is by itself a Boolean expression, which is asking, is f a function where X is a domain and Y is a codomain? So that's Boolean because f as a set may not be a function. So if we want f to be a function, then the first requirement is f has to be a subset between of the Cartesian product of x and y. All right. So I'm going to take row today because I haven't taken row since the beginning of this class. So sign in to Canvas and we'll go ahead and take row. If not for anything else, it's for my own statistics because I want to see whether attendance has anything to do with the performance of this class. All right, so I'm going to unhide this, just sign in, and there should be an activity called row on 2025. And it is, well, I think you guys have enough time. 5 minutes should be more than enough time to sign into Canvas. Go to this activity, go into it. There's no question in this quiz. So all you have to do is to type in the access code, which is bijection, get into the quiz and click submit. You will get a score of 0/0. And that's as high as it can go. As opposed to a dash over a 0, which means that person is missing. So I'll give you guys a moment to do this, and then we'll continue with the discussion of injection, bijection, and surjection. So to the student who is online, can you get this part done?
Yeah, I already did it. Thank you.
Excellent. Okay, I'm just checking. All right. Any other questions? So if you're done with this part already, you can kind of think about questions to ask, or kind of move ahead a little bit to the discussion of injection and surjection, or getting back to what makes a function a function. Yes. Hmm. Yeah. It you can basically describe the expression what it does, or you can use the expression itself, as long as it returns either a true or a false value. Yes. Hmm. A predicate is no more than a function that returns a bool type, bool bool type. Hmm. All right. So assume, does anyone need any more time to complete the row taking activity? We all good there? Okay. So, there's a whole long derivation here, okay? It takes a while to get to this point here because I was explaining along the way how it is derived. So in this case, along with the first requirement, this is the second requirement. The second requirement for f, a set f to be a function, is you evaluate everything that can be in the domain, okay? And for each one, it has to make this equality true. Well, this equality by itself is not very complicated. I'm just asking, is the left-hand side 1? In this case, the 1 is numerical 1, not true. Okay, it's just numerical 1. So this notation is, oh, wait, hold on a second here. What does this mean? The bar in the bar. Cardinality, very good. Which means, we're loosely associating that with the number of elements of a set that is inside the bar notation. Well, we do have a set here. We see the curly braces. It is a set. So this is saying, each element in this set has to be a two tuple because whatever is to, okay, I need to use the mouse pointer now. So whatever is to the left-hand side of this particular bar specifies the format of each element in the set. Okay, it's a two tuple with E as the first member and Q as the second member. The value of E is already fixed. We know E has to be one of the members of the domain. Q is unbound at this point, which means go get whatever Q that makes the other side of the bar happen. In other words, this part here is the actual Boolean expression that constrains what element can be in this particular set. So what we are asking is, go find me, something in F as a set in the form of EQ. But we need to make sure that E is coming from the domain and group all of those things into a set, and then tell me how many things are in that set. I need to have one and only one thing in that set. In other words, for every element in the domain, I needed to map to exactly one thing in the codomain. That's basically what this expression is trying to say. Is that okay? All right. So a lot of the difficulty of this class is getting familiarized with the notation. So the more you look at the notation and the more you dissect the notation and try to understand it, the quicker you get familiarized with the notation. So that's kind of the important part. All right, so that's basically it for this particular module. And then we are moving on to the next module, okay, which is about the words injection, surjection, and bijection. So we're going to get into here. Okay, there we go. All right, so we're going to start with injection. So an injective function, otherwise known as an injection, because it's getting inject from injective, and then the shun, T-I-O-N, from function. So an injection is just an abbreviation of injective function, has each element of the domain mapped to a unique element in the codomain. So this time, this is a requirement on top of what it takes for a function to be a function. So now we are counting three requirements. One, the function as a set has to be a subset of the Cartesian product between the domain and the codomain. First requirement. Second requirement, every element in the domain has to map to one and only one element in the codomain. Third requirement, every element in the domain has to map to a unique element in the codomain. So that's our additional requirement in order to make a function an injection. Every injection is a function, but not every function is an injection. So is that okay? Because I just said a sentence where you understand every single word, but do you know what I mean by that? Every injection is a function, but not every function is an injection, because it takes one more requirement to qualify as an injection. All right. So when we use English to describe everything, just a sec, we kind of all understand what unique means, okay? Or we kind of know what it means. Yes, go ahead. Okay, so let's see how we can express that, okay? So one easy way to express it is like this, okay? So let's check out what this means. For every P in the domain, for every Q also in the domain. So P and Q can be the same, okay? So I'm looking at every single way to pair every element in the domain. This part has to be true. This implication has to be true. So the implication says P does not equal to Q implies blah, blah, blah. So that means when P and Q are actually the same, then the expression that is on the right-hand side of the implication really does not apply, because if the left-hand side of an implication is false to begin with, then the whole implication is going to be true. But what if P and Q are actually different? Then we have to evaluate the right-hand side. Then basically this says if you apply f as a function to P and you apply f as a function to Q, they cannot be the same. And that's how we can define uniqueness of how elements in the domain map to elements in the codomain. Is that okay? Does everybody understand how to interpret the mathematical notation where the mouse pointer is pointing to? We good? Okay. The other way to say that is this thing here. So you guys would go like, haven't we seen something like this already? Well, the answer is yes, but it's not exactly the same thing as what we saw earlier. Because this time, Q is an element of Y, not X. So we are basically saying for each element in the codomain, okay, what do we want? Well, we want this thing here, the entire parenthesized expression to be true. Okay, so now you have to look into the parenthesized notation and go like, okay, what are we doing here? It is a comparison. I'm looking for something, I'm looking, I'm evaluating whether a particular value is less than or equal to 1. Okay, yep, that are not mapped to by anything in the domain. Yep, that is correct. So it can be 0. Okay, so there may be some elements in the codomain like, okay, no one from the domain maps to me. That's perfectly okay. It's not a problem. Okay, but it has to be less than or equal to 1, which means it can be up to 1. In other words, in this case, it means it can be 0 or 1. So what are we counting? What has to be less than or equal to 1? Well, it is the cardinality of a set. So now you ask, what qualifies to be an element in this particular set? Every element in this set is in the form of a two tuple, PQ as items inside the two tuple, such that, okay, this middle bar means such that PQ is an element of F. That's all it is. Now, in order to apply this, we need to know that F is a function to begin with. So it has already passed the test of F being a subset of the Cartesian product between X and Y. We already know that every element of X maps to one and only one element in Y. We are only asking, are they unique? Is that okay? All right, so let's take a look at some examples because I think examples can help us understand or verify our understanding. And this is one thing that I kind of want to mention too, is whether people are learning from the example. In other words, the abstract description is completely over the head, and they're only looking at the examples to try to extract the abstraction from the examples. Or are people understanding the abstraction already, and they're using the examples to verify their understanding? Okay, so those two approaches are very different. Okay, and I'm not going to say which one is better. Okay, but one of them has more room for error. In other words, one particular method means, you might end up with an understanding of an abstraction based on the examples, but your abstraction or your understanding of the rules may not be complete or may not be entirely correct because there are some tricky examples that you have not seen to illustrate a particular aspect of what you're learning. But the other way around means you're understanding the rules to begin with, and you're just using the examples as a verification that, oh, okay, I can figure this out. I know how what the answer is supposed to be. So most people learn by a mixture of the two, but which way you need to shift in order to be successful in this kind of a career is you need to understand the rules first, okay, and then use the examples to verify that your understanding is correct. So anyway, I'm going to present some examples here. So we are looking at, okay, X is ABC, A, comma B, comma C. We are looking at Y being um, 1, 2, and 3, okay, just to make it easy. And now we have some examples. Okay, so this time I want F to be A1, B3, and C2. Okay, so now the question is this an injection? What do you think? Okay, so the way we look at this, there are a few ways to look at this. You can look at this intuitively and ask, um, do A, B, and C all map to unique elements? Okay, using just your natural understanding of the word unique. You go like, oh, okay, A maps to one. Okay, let's see if anyone else is mapping to one. Nobody else is mapping to one. We're good. B maps to three. Is anyone else mapping to three? No. And C maps to two. Is anyone else mapping to two? No. Okay, is this a subset of the Cartesian product between X and Y? Yes. Is every element of X, with being A, B, and C, mapping to one and only one thing in the codomain? Yes. Okay, so it meets all the requirements. So the answer is yes, this is an injection. Okay, so I'll just say true. Okay, so that's one way to look at it. Now, I'll give you an example where it is not an injection. All I have to do is to do something like this. So now you ask the question, is this one an injection? Okay, let me fix the answer first. Get rid of the answer. So now you go through the same motion and go like, okay, A maps to one. Is anyone else mapping to one? Nobody else. Okay, so that's unique. B maps to two, and then you ask, is anyone else mapping to two? Oh, yes, C is also mapping to two, so it's not unique anymore. So this cannot be an injection, and it is false. But it is also helpful to look at it from the mathematical notation, and then you're really asking, if I just look at one, as a member of the codomain, I'm asking how many things are mapping to one from the domain. We can see that A is mapping to it, and that's it in F. So it meets the requirement of at the most one. Okay, and then we can look at three. Okay, we'll look at the element three of the codomain, and then we ask the same question. So you ask how many things are mapping to three. You look through F and go like nothing. Well, it's okay because nothing, which is zero, is less than or equal to one. That is still okay. It is only when you look at two as a member of F, oh, excuse me, as a member of Y, the codomain, then you go like, oh, hold on a second here. There are two things, B2, C2 as tuples. They are both mapping something from the domain to 2 as an element of the codomain. So the cardinality of the set that we were talking about earlier would be 2. And then you're asking, is 2 less than or equal to 1? The answer is no, it is false. So that means at least one element in the codomain is mapped from more than one element in the domain. And as a result, the universally quantified expression is false. In other words, this whole thing is false because this portion from this bar all the way to this bar evaluates to 2, and 2 is less than or equal to 1 is false. But this entire thing is inside the universally quantified expression, which means the quantified expression, the whole thing, is false because there's one thing, at least one thing in Y that makes the parenthesized expression false, which is that part here. Is that okay? So that's injection. Now we can talk about surjection. I'm just looking at the time, making sure that I'm not using more time than I need. Yep. It's called bijective. And that's one reason why you need to read ahead of time. Is a bijection is a function that is both injective and surjective. I like the fact that you are projecting ahead a little bit, okay, what if it's both? Because it seems like it can be both, but it's also important to read ahead of time so that at least you understand what terms we are talking about. If you compare the material of a class as a forest, okay, it is good to get a layout of the forest ahead of time, okay? Because in class, we are not going to spend as much time to take a look at the map of the entire forest. We'll be zooming into a particular tree on a particular branch, and sometimes we'll count the leaves on a particular branch. Not talking about the programming kind of tree. I'm literally talking about the tree. Okay, so it's easy to get lost, okay, when you're only looking at the pine needles of a pine tree. So reading ahead of time, to learn about the layout of the material means that you kind of know where the discussion is. You know kind of where you are in the forest anytime when during the lecture. And I think that is important. All right, so here's surjection. The natural language description is a surjective function, aka also known as a surjection, is a function where every element in the codomain is mapped to. That's all. Okay. How many times does it have to be mapped to? Doesn't matter. Okay. It can be one, can be two, can be three. It just cannot be zero. So the following statement is true for a surjection. X is the domain, Y is the codomain, in addition to the requirement of being a function. So let's take a look at this one here. Yes, go ahead. If that is true, then it is a surjection. Yes, it's guaranteed a surjection. Yes, because that's the only function you can get out of that domain and codomain. Okay, so we are looking at this particular statement here. What is it saying? Okay, so we have to interpret what this is saying. It is saying for every Q as a member of the codomain, there exists a P in the domain such that f of P equals to Q. That's all it says. Okay, and that expresses the same thing as the natural language that says the earlier part, which I can highlight. Okay, is a function where every element in the codomain is mapped to. So because we are looking at every element in the codomain, we're asking, can I find at least one thing in the domain so that the element Q from in the codomain is the result of F applied to P? I just need one, okay? If there are multiple, that's good. If there's only one, that's good too. But if there's none, we have a problem. Is that okay? So that's one way to look at it. But then the other way, the equivalent way of looking at it is this expression here. You guys go like, but that's almost exactly the same as the one before. The other one before has a less than or equal to one. This one is greater than or equal to one. That's the only difference compared to the one before. So now some people may be asking, so why do we translate something that is slightly more intuitive to something that is not so intuitive? Well, the reason is we have to talk about bijection. So bijection means something is both an injection and a surjection. So that means both of these two conditions have to be true. Okay, so I can show both at the same time. So we are talking about this one and this one. They both have to be true. But you can see whatever is inside the cardinality is exactly the same. The only difference is the comparison operator. One needs to be less than or equal to 1. The other one needs to be greater than or equal to 1. So we are really asking, is it exactly 1? Does that make sense? Because when you have a conjunction between this and this, the only thing that will work is to change this comparison to an exact equality. Because what can be less than or equal to 1 and greater than or equal to 1 at the same time? 1 itself. Yep, that is correct. That's also a good way to describe it. So that's basically what a bijection is. So the explanation of the bijection is, oh, okay, just change that comparison operator to equal to, and we are good to go. Then you go like, wait, hold on a second here. Isn't that also the same thing to describe what a function is, what it takes to be a function? Well, not exactly. Because when we look at this whole thing to describe what a function is, we are looking at every element of the domain. This is from the other perspective of every element in the codomain. That's the only difference. Okay, which means from the perspective of everything, it really just means are we targeting the first member of the tuple or are we targeting the second member of the two tuple? That's the only difference. So that means, hmm, so that means the description of what it takes to be a function and what it takes to be a bijection is almost symmetric. And I'm using the term symmetric in a very loose way here, okay? Because it's just, are we talking about a first member or are we talking about the second member of the two tuple? Okay, so the consequence of a bijection is an inverse function has to exist. Okay, if you have a bijection, then the function f is a function because otherwise there's no way to describe it as a bijection. But there has to exist an inverse function. So the way we describe an inverse function is this. For every element in X, which is our domain, f inversed, okay, this is the inverse function of the result of f applied to E is just E. So the concept of inverse function probably is not new to you because all of you have taken pre-calc, and I'm pretty sure they talk about inverse function either in that class or classes before that. Okay, so inverse function is guaranteed when you have a bijection. So it is kind of neat in a certain way because this means if you can map from this set to this set here, if I know where you land in the codomain, I can reverse the process. I know exactly where you start. Okay, so let's think about this. I know we only got about a minute or less. So think about this for a moment. In cybersecurity, okay, the password that you set up for any account that you have is stored as an MD5 hash, okay, in the good old days. So these days they use a much longer hash value, but nonetheless, it is just a hash value, which means there are multiple passwords that can map to exactly the same hash value, okay? So yes, you can use salt to help kind of mitigate the problem, but it can only go so far. Okay, so that means if somebody has a lot of processing power, and they basically just test all the character combination to see if I put in this character combination, it generates this hash. If I use this combination of character, it generates this hash. If somebody can exhaustively generate all the hash values, then they can reverse the process and find a string that will be usable to log in, even though it may not be the same string as your original password. So that is not a bijection, okay? Because there are multiple strings that map to the same hash value, okay? But the hash values are really long, and it takes a long time to generate that table. So that's the only way. That's the only reason why it is still considered semi-secure. Yes, go ahead and you. Yep. But it is not feasible if there's a huge number of hash values. So MD5 is limited. So that means, if you get the hash value, you can reverse back to what string will pass, and there are not too many. But when you look at SHA 256, that's huge. Okay, so it is not feasible, on computers today to make that table. Yes, because when MD5 was first used, we had computers that only have hard drives of 5 MB. Good luck, storing the entire rainbow table, right? But now we have, easily terabytes of data on a hard drive, so so it becomes defeatable. Yes, yes, they have to be. In fact, no injection does not need that. So it has to be bijection. Yeah. So you can only say that in a bijection, the cardinality of the domain must be the same as the cardinality of the codomain. Hmm? No, you cannot. Because the surjective function can go in many ways. Because in order for something to be surjective, all you need is to have more members in the domain. You have at least as many members in the domain as there are in the codomain. because multiple things can map to the same thing in the surjection only, right? So they don't need to be the same. Yep. Alrighty. So you guys have a nice Tuesday. Because we will see, I will see you guys on Wednesday, and then be more of this stuff. Yes, let me stop the recorder. Stop share. There we go. And end the meeting. Thank you.